in terms of signal to noise ratio. Okay. Now, let me move to Japan and to extend the discussion about MRLs, because in Japan they're using MRLs for pesticides, veterinary drugs, and also for feed additives. Lots and lots of testing going on with feeds and grains, because those become food products for beef and other animals. Now, I've talked a little bit about the positive list. I've told you about the MRLs, and I've told you about their limits of detection for MRLs, which get down to subpart per billion levels, so they're really quite low. Now, rather than talk about pesticides, let me give you an example. And I apologize, this slide is not in your books, and I apologize. But I'll get back to you. I wanted to show you the structure of some of these veterinary drugs, and I chose to talk about nitrofurans. Now, these are the nitrofurans that are used as veterinary drugs, and as you can see, they're all nitrogen bases. But what happens is, as the animals ingest, now this could be shrimp, it could be fish, it could be beef, chicken, pork. As they ingest these nitrofurans, they metabolize the nitrofuran, and they metabolize the metabolite is shown here in this structure, which simply means that you broke this nitrogen-carbon bond and protonated that right there. So what you want to analyze for is not nitrofurans, you really want to analyze for the metabolites. Now, what's standardly done in this technology is you then take the metabolites and you do an overnight derivatization reaction, and the derivative of the metabolite is shown right here. Okay, so now let me go back to the first slide and show you the method here, because I wanted you to see what we're doing with these nitrofurans. This is an example of taking a crawfish. Now, crawfish has a high salt content, has a high protein content, a high water content, and those are all major interferences. Plus, it's structurally very complex. It's not easy to homogenize crayfish because of the nature of the meat and the interstitial materials. So, if I start out with the crawfish here, and then simply do an acid homogenization and digestion with HCl, and then you use DMSO to actually force the derivatizing reagent into the structure of the crawfish with the derivatizing agent, which is 2-nitrobenzaldehyde. Okay, so the benzaldehyde is exactly why you saw the derivatives of the metabolites. And then what you do is just put this in a warm oven overnight at about 37 degrees, and you let this derivatization reaction run with the accelerating agent being the DMSO. Okay, now the next day you do a couple of liquid-liquid extractions, and then you evaporate the sample down to dryness so that you now take it back up in a solvent that's compatible with HPLC. So in this case, we're going to use a water-methanol mixture so that we can run HPLC, MSMS. Okay? So now we're going to use a triple quad mass spectrometer with an HPLC. And I wanted you to see that once again, we're banking on the high specificity of the detector to give us a relatively simple sample preparation method. Now, that sample preparation method basically takes overnight because you have to run the derivatization reaction. But in terms of working time in the laboratory, you can work through that in about an hour. Okay? Now, at the Food and Drug Laboratory in Los Angeles, California, which is a routine testing laboratory, what happens is that then in the morning, when you come into work, if this gentleman is the first person in, the laboratory gives him a head of lettuce and says, analyze this head of lettuce today. When you're finished, you can go home. And the next person coming into the laboratory, they say, okay, here's a piece of fish. You analyze the fish, and when you're done, you can go home. And so on and so on. And they have about 60 chemists working on 60 different samples every day. Now, what happens is the chemists know that if they come into work at 6 o'clock in the morning in the laboratory, that they will typically spend 6 to 8 hours doing sample preparation, especially if you had the salmon, right? Okay, he had the salmon. So it's going to take 6 or 8 hours just to do sample preparation. It's going to take him an hour to do the GC mass spec analysis or the LCMS analysis, and another hour to run the blanks and the check samples and do quantitation. So these people have been there 9 hours. That's why they came at 6 in the morning. So along about 4 o'clock in the afternoon, they get to go home. What happens if they come to work at 9 o'clock in the morning? They're there all day, and they don't even get to eat dinner because they're still there in the evening. Those are the methods that are very, very time-consuming, and those are the classical proven methods. And that's why we're trying to help you understand that there's many new ways to analyze these samples, and a lot of it comes down to sample preparation, as you can see. Okay, so these methods give you excellent quantitation, excellent linearity, and we'll talk more about that today. I'm going to skip over melamine for a minute because Guiping is going to talk about melamine. And let me go right to trace metals, because trace metals are also regulated. The trace metals are also regulated in the European Union, and there's 3 important documents for you, and those 3 are listed here. The first one deals with regulations of all kinds of foodstuffs. And the only thing that you're required to test for in foods and foodstuffs is lead, mercury, cadmium, and tin. There's another one that talks about MRLs for foods, for food additives, and for food supplements, things that you add to the food for preserving food or for improving the flavor of food or the smell of food or the taste of food. And those are lead, cadmium, and mercury. And those are really the big 3, lead, cadmium, and mercury. When you get over to animal feed, now remember, animal feed is an agricultural product, and John Gilbert talked about the whole food chain. So when you have animal feed and food coming through agricultural products, then you also have to look for things like arsenic, for example. Okay. Now, again, in the same vein, there's a couple of directives I would point out to you that come from Europe. The first one is right here for your reference, and it talks about how to sample these various different types of foods and foodstuffs and grains and so forth. And it gives you the performance criteria for the metals. And this one over here does a similar thing with methods for multi-element determination like ICP, OES, and ICP mass spec. Okay, inductively coupled mass spectrometry, inductively coupled plasma mass spectrometry. Now, to give you an idea of the simplicity of these methods, let me show you a sample of a method that was developed in our laboratories in Cambridge. And what they decided to do was to try to see if, in fact, you couldn't do an analytical determination for 10 or 15 or 20 different metals all at the same time and comply with the EU regulations. So the elements that were chosen are all the ones that you heard about, like arsenic, for example, and cadmium and so forth. And so this was done with ICP optical emission spectrometry. Okay? The beautiful part of trace metals is the sample preparation is much, much easier. So whether it's any dietary supplement or whether it's a grain or an agricultural product like wheat or like a biological material like liver. And if you've ever want a difficult sample, try the analysis of livers and kidneys. They are very complex to analyze because they're also very heterogeneous. All right. But just like most spectroscopic methods, if you do a nitric acid digestion in a microwave digester, you basically have done the sample preparation, except now you get to do a dilution. And this is the big change. Here again is an example where you have an extremely sensitive detector, and that's the ICP. And because it's so sensitive, you don't have to do a lot of sample preparation. The real sample preparation is done by dilution with a solvent. So in fact, if you can dilute the sample, you also dilute the interferences. And that makes it much easier to do the analysis. So I think that the best sample preparation method is no sample preparation, just being able to dilute the sample. And the way you do that is you have to have very high sensitivity in your detector. Now, as you can see, for example, our results ran in the part per billion range, and the European MRLs are in the part per million range. And in fact, with this analysis and this method, we're running with about a safety factor of about 50,000 times more sensitivity than is required to meet the EU method. About 50,000 times more sensitivity. Well, it's kind of interesting. Just as I was leaving California to start this trip, there's an article that appeared in the news, and it says that the government of New Zealand has now found lead. This is the New Zealand Food Safety Authority, has found lead in breakfast cereals and in baked goods, cookies, cakes, bread, and there's lead all over the place. Now, you know, in New Zealand, if you've been there, it's a very pristine environment, and New Zealanders have never tested for lead in their food before, and now they're finding that, in fact, there may be toxic levels of lead in certain grains. So as a result, they're now quadrupling the level of effort in New Zealand to test for lead in these grains. Another example is from a United States newspaper that I tore out. This appeared in June of this year, and the headline says, quote, "All fish caught in the United States freshwater streams contain mercury." I was horrified. All fish caught in any freshwater stream anywhere in the United States is now found to contain mercury. How did they do it? They did it exactly this way. Now the problem is you got so much sensitivity that in fact they've caused people to be very alarmed because they've got so much sensitivity that now you can find mercury in soil or water or fish, and in fact it's really nowhere near the toxic limits. But when my wife saw this newspaper article, she said, "Oh my, I'm not buying any more fresh fish in the United States." So we now, in our house, we import fish from Alaska, and we have it flown in because you can get it shipped in every day. Okay, so it just shows you that the people are learning more about the food that we eat every single day. Now, I'm not going to stop to talk about speciation today. I'll save that for a future talk. What I'd like to do is close with something that John Gilbert touched on, and that's mycotoxins. And mycotoxins are quite challenging because they're large, complex molecules. They're not necessarily thermally stable, and they lend themselves, obviously, to LC, mass spectrometry. Now, the method I'm going to show you here was done in a laboratory in Prague, in the Czech Republic, by the food science department there in Prague. And what they did was to ask the question, could you determine more than one mycotoxin in beer if you used a mass spectrometer with very high mass accuracy? Now, John Gilbert talked about analyzing for one mycotoxin at a time. Now, we're talking here about looking for as many as 8 mycotoxins at one time in beer. You say, why beer? Well, how did mycotoxins get in the beer? Mycotoxins are formed from grains, and all the beer is made from grains and barley and rye. And so if any of those grains contain mycotoxins, that's going to transfer into the beer. The other reason this is important is because the favorite food in the Czech Republic is beer. The second favorite is beer. And the third favorite is more beer. Okay. So it's a very important problem for them, and they're very concerned about the quality of their beer. So we said, let's look and let's just do a screening experiment using this method to see if we can detect mycotoxins in Czech beer. So that method is outlined here, and you can see it's 20 milliliters of beer. You do an extraction with acetonitrile, and then you have to evaporate that extract down. Now basically all you've done is do a single liquid-liquid extraction, and you have to do a filtration, obviously, to remove the suspended materials and the particulates out of beer. And then you just take that beer extract up in a methanol water mixture and analyze it by LC mass spectrometry, LCMS. Except this time the mass spectrometer is the so-called exactive mass spec. An exactive mass spec will identify unknowns for you at up to 5 or 6 decimal places in the molecular weight. That's why it's called high mass accuracy. When you look at the analysis of these peaks in the spectra, you know, if you have the molecular weight to 5 decimal places, it's unambiguous identification of unknowns, because there aren't duplicate compounds that we know of that have the same exact mass. Okay, so this exactive mass spectrometer is a very high specificity detector, and it also offers the advantage of being able to do screen a method so that you don't have to use, for example, affinity columns. John Gilbert talked about using affinity columns. There's no affinity column in here. This is a straight reverse phase column because it's an aqueous sample. Now when you look at this sample and you screen that, you'll see the results look like this. And first of all, the entire analysis is 10 minutes in length. The sample preparation was about 6 minutes because it's just extraction filtration. Okay, so it's pretty fast. Now I want you to see the extreme specificity of these mycotoxins. And in fact, what we found were 8 different mycotoxins because we screened for 8 different mycotoxins. And those peaks are these right here. There's peak number 1, 2, 3, 4, 5, 6, 7, and 8. And you see that they're all resolved to the baseline, and the peaks have all been identified according to their exact molecular weight. So there are no interferences in here. Even though it's a screening analysis, you don't see any background peaks. You see only those compounds that you're actually looking for with an extremely high accurate mass. Well, what I've tried to show you in a few minutes here is that things are changing quite a bit. You're seeing more multi-residue methods. You're seeing people in Latin America, especially in Brazil, doing things like trying to combine testing for beef and horse meat in the same sample. Also looking for multi-residues in mixtures of fruits and vegetables. I think you're now going to see a lot more interest in screening analysis with untargeted compounds. I think that happened because of melamine. Melamine was never a targeted compound. Never was a targeted compound. It was found only because thousands of children in China got very ill. And so people started looking for true unknown